So, hello everyone. Uh, we are pleased to welcome Saurabh Sharma. He is a research scholar and Prime Minister Research Fellow at IIT Patna in India. His research focuses on advancing knowledge distillation techniques with a particular emphasis on architectural innovations and loss functional strategies to improve the performance and efficiency of machine learning models. So Saurabh was awarded with the MICCAI RISE grant to present his research last year at MICCAI 2024. And today he will share his work as a part of the MICCAI RISE Journal Club. So the presentation is titled Confidence Matters, Enhancing Medical Image Classification through Uncertainty-Driven Contrastive Self-Distillation. So I leave it to you, Saurabh. Thank you so much.
Yeah. Thanks, Alvaro. Hope I am audible and my screen is visible. So, welcome all to my presentation on confidence matters, enhancing medical image classification through uncertainty-driven contrastive self-distillation. I am Saurabh, research scholar at IIT Patna. So, this paper was actually accepted at MICCAI 2024, and so let's come to the things what I have to discuss. So basically, the work is all around model compression and its uses in real world, where knowledge distillation is the prevalent technique, and also uh, there are some concepts I would like to introduce first. Then I will go to the overall methodology. So coming to the model compression, so in real world. We want to deploy large AI models in the smart devices like smartwatch. We have some IoT based devices, some smartphones, some smart TV, or some any kind of autonomous vehicle. And those large AI models cannot run efficiently on edge devices. Like there are some resource constraints, like these devices you can see on my screen. So in real-time applications, we want some low latency responses and also some efficient uses of the model within some resource limit. So that's why we use some model compression techniques. Some of the prevalent techniques are pruning, quantization, we have weight sharing, tensor decomposition. There are a lot of, and knowledge distillation is actually one of them. So when we compress the model, we actually ensure that the power, the space, the memory, all the things are actually utilized in an optimal way so that we can get low latency. We use some less resources so that we can deploy multiple models at the same time within the device. And also, there should be some power limitations as well. So we want to ensure this with the model compression technique. So coming to the next part, what is knowledge distillation actually? So knowledge distillation is actually here it's a prevalent concept in terms of deep learning, and now it is used in multiple areas like computer vision and NLP, and also for graph learning. So in this, we have two models. We have a cumbersome model, which is teacher model. We tell it as a teacher model. And there is a lightweight model, which we want to deploy on a resource constrained device. So we actually can train the student model using the data we have. And the problem is that due to some less number of parameters, this model may not be able to learn efficiently with the help of data only. So what we do, we actually take the help of that teacher model. We actually do a kind of regularization. So with the help of that regularization, we try to create an failover alternative of that cumbersome model. So we will actually train the teacher model then with the help of that trained teacher model, we actually try to regularize the student model which is in training. So the final model we get is a distilled student model, and that will be actually working alternative to that teacher model, maybe better than the teacher model. It is also proven in the recent trend. And with the help of that, we want a deployable alternative of such cumbersome model. And the major part, what we want to enhance for this process is actually the knowledge and the dark knowledge. So in the first ever paper where Hinton actually provided this concept, there is a concept called knowledge. So knowledge is actually any learning that models acquire from data whenever we actually perform a specific task or set of tasks. For example, here you can see we have some input X. It's some kind of data or augmented data sample. We actually train the teacher model with the help of this. So the learning at each layer is actually a knowledge. At the end, it is also a knowledge. And if we want to apply some kind of loss function or any kind of feature to extract some knowledge, some kind of feature from this or attention from these layers, that will also be calculated as a knowledge. Then there is a term called dark knowledge, which actually contributes more in case of knowledge distillation. Dark knowledge is actually any information which actually is learned by teacher and that contributes to its input. For example, if there is some task and teacher is providing some output for that, so dark knowledge is we can say is kind of reason why it is coming to that output. Knowledge is some kind of thing, we can say the output itself or the soft output, that is when we apply the softmax on logics, we get soft logics, we can treat it as a knowledge, we can extract any intermediate feature, we can tell it as a knowledge, but the dark knowledge is the reason behind that. So we actually try to provide an alternative model from a dedicated cumbersome model using that dark knowledge. So we first extract the knowledge and dark knowledge more and more, make it relevant for the transfer, and then transfer to the lightweight model. And that lightweight model will be deployed to a smart device, or we can say edge device or some resource constrained environment. Next come, it's a kind of analogy we can say. Here is a data, say here's a teacher model, here's a student model. So data can be treated as a book where we can actually take reference from. There is a teacher which actually teaches that it is a dog. It's kind of a data from book. In book it is written that it's a dog, but a student, due to its low calculation power, is not able to recognize that it's a dog. So teacher will tell it's a dog. That's why student will tell it's a dog now. Okay. So with the help of data itself, a student was not able to learn. That's why we need a teacher so that it can make more confidence for a student to tell it as a dog. Next comes is the contrastive learning concept. So contrastive learning is a kind of learning where we actually try to learn meaningful representations with the help of some functions, some similarity functions that actually brings similar samples closer and dissimilar samples are pushed apart. For example, here we can see there are positives, there are negatives, and in this we actually take an anchor, which is actually a sample itself, and based upon some similarity, we can use some contrastive loss techniques like triplet, like influency, like cosine similarity, negative cosine similarity, that we will take, and with the help of that we will actually just apply contrastive learning, and we can say a kind of cluster these nodes or these data samples where anchor will be combined with the positive sample and the other negatives can be grouped together or in different negative samples like this. Sorry. So what this learning does is that there is an anchor, there may be negative and positive nodes or samples. Based upon some similarity or some loss, we will calculate. We can just uh, push this negative part and pull this positive closer to the anchor node. So that is the actual meaning of contrastive learning. We will use it in our proposed framework. Next is there may be different kind of contrastive learning. So one most used is self-supervised contrastive, where we actually have anchor node. We have augmented data treated as positive node, and based upon similarity, we just apply. We can get some negative and positives. So the problem is that we actually don't consider any label information in this kind of learning. So the problem we face during the inference is that we actually can misclassify the data samples. For example, you can see we have this dog in this picture, okay, and we have negative negatives these dogs, but it's a dog only, so it should be classified within this cluster. But due to self-supervised contrastive learning, it may actually maybe actually misclassified with this negative sample. So to tackle this, uh, new concept was introduced, I think around 2004. So it was supervised contrastive learning, where we actually use this label information. So we what we do here, we actually augment the data first and take all the positives with the anchor, and from that set of data, we actually do the contrastive learning. That is similarity for next, we can say, other samples which can be treated negative and positive. So supervised contrastive learning actually extends contrastive learning by leveraging label information. So it actually groups the samples of same class closer in the representation state, and it actually forms the positive pairs, and that is not actually limited up to the augmented views. Like here, the positive sample was in augmented view only. It's a augmented data of this image only. So here we have, with the augmented one, we have another one or another set of positive data which can be treated in the positive class. So in this, the main thing what it introduced is the supervised contrastive loss that will also be used in our study. Next is non-parametric learning. So there are two kind of learning. First is parametric, the second is non-parametric. So in this paradigm, uh, it's kind of unsupervised learning approach where we actually feed forward the neural network with the image of some classes, and we don't care about the number of parameters or any constructing function which maps input to output. We actually provide, we can say it as a feed forward network where we actually provide this image to a higher dimension, then to a lower dimension, or we can normalize it, or we can apply any function on that. And with the help of that, we actually uh, just normalize overall set of data in some limited dimensional unit hemisphere. So the advantage of such kind of learning is that it provides more flexible outcomes because we are not carrying set of parameters needed, and as there are no assumptions, so it will provide us a better model. So in this, what we do that we are actually taking the image and we are kind of extracting the embeddings, uh, or we can say a group of examples for particular class, and we actually store it in a memory bank. How we will use it, I will discuss in later slides. So the main task on which this paper is actually, it is medical image classification, where we actually uh, the task is to assign labels to the medical images to aid in diagnosis and treatment planning. So in this, mostly we apply deep learning models, which are actually trained on some annotated data sets, and that may not be annotated in case of newly born diseases. And the critical things we want is high accuracy and robustness uh, for clinical decision making. So the main challenges we face is that if there is some kind of newly born disease, we may not have such uh, accurate data on which we can apply some deep learning models, or we can say that medical field is very uncertain about the data, because most of the diseases look similar, or similar disease examples may look dissimilar. So there are multiple unique challenges we can face in medical image classification that uh, creates challenge for the technique also, and for any kind of classification also. So some existing challenges I have listed down. First is the class imbalance. Like if uh, we are considering some kind of a part of our body, say we are considering eyes. So if we are scanning some um, scanning for some diseases we want to classify, and there may be a chance that we may get a very high number of examples for certain class and very low number of examples for certain class. Like you can see here. Okay, so we have 7 classes, but what we can see is that more than 5,000 examples for one class and only 37 examples for sixth class. So this kind of situation we can face in medical image analysis or medical image classification also. Then there comes inter-class similarity, where we have two different classes and both look similar. Like if we see by naked eye, we can see that these two diseases are little closer to each other. If we just remove the hairs from this and just apply some brightness, we can go through this. But these two are different diseases, same for these two. So these four are different kind of skin cancer examples, and these two actually look similar. These two may look similar based upon different examples we can extract from data. And there is intra-class variance, where a single class example may actually look different. Like it's a moderate class of aptos, that is a diabetic retinopathy data set. So these eyes are for similar class, but these are looking very different from each other. But these belong to same kind of disease or problem. Then there is data scarcity. As I earlier mentioned, that due to a very uncertainty in this field, we may not be able to get data for particular disease. So that creates data scarcity. There may be noisy labels due to human errors, and there may be corrupted data also due to, we can say, some technical fault. Then there is data privacy, because we cannot disclose the patient full summary, um, full treatment summary, we can say. Then there is data distribution, how data is distributed among the classes, like you can see here also, and data is scattered here. Then there is data heterogeneity. So data heterogeneity is a concept actually covered in the previous session also, and it's kind of the problem where data from some class is missing totally. So these are some existing challenges in medical image classification. Now, what we are using is knowledge distillation. So there should be some existing challenges for knowledge distillation also, which may motivate for us for its improvement. So knowledge distillation actually wants knowledge and dark knowledge, mostly dark knowledge. So for this, we actually extract the knowledge from different sources. Say we want to transfer the knowledge we have learned from the logics, or we can say the outputs, and we also want to utilize the intermediate knowledge as well, the dark knowledge. So knowledge from one source may not be coherent to the knowledge from another source. That is the problem, that uh, from one source we are learning and other source is actually decreasing the performance. So we want coherent transfer of the knowledge. Second is class imbalance and the other challenges uh, that may lead to the class bias or other unique problems, because the teacher will learn from that data only, which is already provided. So if teacher gets biased, then the student will also get biased. Then third is the learning behavior may propagate to the student from teacher. So that we should be ready for. And unavailability of dedicated teacher model. So as we can say that uh, in medical field there may be newly born diseases. So getting a dedicated teacher model which we can assure that it will work, that may not be possible. So with these, the motivation and the objective of my study was uh, that employing diverse method for knowledge extraction and knowledge transfer may lead to enhanced performance and regularization of model. Okay, so what we have done, we have actually extracted the knowledge through different methods in the same framework. Then second is we have adaptively transferred the knowledge. So adaptive transferring of knowledge actually can ensure a kind of coherent knowledge transfer. So like the paper's name is confidence matters. So we have calculated the confidence of each model before transferring the knowledge from one to another. Then confidence from multiple learning methods can increase the certainty that a sample belongs to a specific category. So for example, if we use two paradigms, say contrastive learning and supervised learning only. So if two methods are providing me uh, some kind of output where some sample belonging to uh, same category with the help of both of the methods, then we can say that we should be confident enough that this sample belongs to this category only. So the objective we have found that is to establish an efficient framework where the model regularizes uh, by leveraging diverse views or learning approaches to address the mentioned challenges. So the challenges are some challenges from these um, knowledge creation purpose, some from the medical image analysis purpose. So some of the glimpse of previous works. So in previous works, there was distillation from inter-batch relationships. There was contrastive knowledge preservation. There was relational knowledge augmentation, and there was contrastive knowledge and relational self-supervision. So what was done there, that uh, some batch of the samples are extracted, and the relations were extracted from those, and that relation was transferred. Contrastive learning was done, and then we extract the contrastive learned features and then transferred it. Then for relational knowledge, uh, we augment the samples and then form the relations in some ways. And there were some of the methods where contrastive and relational self-supervision, there were some challenges that uh, if there is significant class imbalance, then positive samples can lead to a divergent behavior. Okay, so uh, there may be class bias, as I have earlier told, and learning may be slowed down because if there is a high fraction of positive samples, then there is a great chance that um our model is able to recognize for one class only. And self-supervised learning based methods, there is always a chance of misclassification, as I have earlier mentioned, and there is vulnerability that stems from inherent nature of self-supervised learning, which does not utilize explicit class labels. So, dealing with these research gaps and challenges, we come to this framework we proposed, that is uncertainty-driven contrastive self-distillation framework. Uh, we abbreviate it as UDCD. So it is published at MICCAI 2024. The challenges we have faced and we tackled in this paper is: first is class imbalance, second is interclass similarity with intra-class variance. So the problem is that these two actually coexist in medical data, and for knowledge distillation purpose, it is also challenging because we uh, need to utilize different knowledge sources, because utilizing only one source or one way of knowledge may actually lead us to a class bias result. So what we have done, we have extracted supervised contrastive features in the mean teacher self-ensembling setting. Mean teacher self-ensembling setting is actually prevalent in this field when we apply knowledge distillation, because there is no dedicated teacher model confirmed for most of the diseases. So in mean teacher self-ensembling, what we do is that we actually use the student model as a teacher model, and one model, one student instance will be training, and second, the one we want to use it as a teacher will update its weight from moving average of the weights of that in training student model. So why it is useful? Because whenever uh, the model gets biased towards some class, normalizing the weights and taking moving average will actually diminish or decrease down the effect of class bias for particular example. So we actually haven't done anything on mean teacher self-ensembling. Instead, we actually extracted more and more features and more ways which can be actually abstraction using this setting and adapt to knowledge transfer. So in our contribution, we have extracted supervised contrastive features. Then there is adaptive transfer of using uncertainty. Then there is the extraction of secondary dark knowledge, and that is done using contrastive learning. And then from different diverse learning, we actually calculate the confidence of different models, and then we transfer it for back propagation. So we have got 5 to 14% better performance than existing state of the art in different performance metrics. So it is the link to the paper. So first I want to introduce the key innovations we have done. So for this, we have actually introduced three things. First is contrastive relation matrix. Second is relational alignment of the learning we are actually getting from this contrastive relation matrix. And third is actually the adaptive knowledge transfer. So in contrastive relation matrix, what we have done is that we actually utilize the supervised contrastive embeddings which we have learned non-parametric memory. get a matrix which we are treating it as contrastive relation matrix. So say we have a memory matrix which is of dimension n cross f. F is the size of projection head we are applying. So you can see here we have a memory, we have n cross f matrix. N is number of class, F is the dimension, and we are actually learning the supervised contrastive learning embeddings using V size batch, and we actually normalize it to F cross F embedding again. So we have actually obtained the memory matrix, we have actually obtained the supervised contrastive matrix, and when we just multiply these two, we are actually getting contrastive relation matrix. So the relation is between the contrastive learning and the non-parametric learning. We have actually extracted this kind of matrix where we are aligning contrastive learning and non-parametric learning. Then for this, we have actually extracted anchor of ith sample class and then calculate the relation to create this contrastive relation matrix as shown. Then there is relational alignment of these contrastive relation matrix. So for that, we have actually extracted the relation among the contrastive relations in this matrix using Huber laws because it is flexible and robust for knowledge transfer and relational alignment because in case of MSc, when there is a high loss, it actually overshoots. So for high losses, it actually uses mean absolute error. So we actually emphasize the relative distances among distribution gap, which is actually done in case of traditional knowledge distillation. Then after doing these two, we have actually applied the adaptive knowledge transfer, where we have applied uncertainty on the different sources so that the relevant knowledge or a fraction of knowledge which is more relevant for better performance that only can be transferred. So here we have overall framework where we are having the input images and we apply the augmentation on these images. So this is a student encoder and the same encoder we are using as a teacher, and this student will be learning. Based upon its learning, the weights of this teacher model will be updated using exponential mitigate the issue of overfitting that may be raised due to class bias. So we actually apply projection head on top of this, and this also to learn the supervised contrastive embeddings. So say for V size of matrix for this and for this also, then we are having a non-parametric learning where we are actually extracting the memories using the concept of non-parametric learning, where we aggregate the samples from each of the class. If we are having n classes, we pass the images through the encoder and just aggregate them using average or any other kind of statistical method to get this kind of embedding. So the main thing I want to discuss is that because the dimension of this should be f and this should be f, so that we can actually align these two. And after aligning, when we want to transfer this, we actually transfer by applying teacher's confidence factor, that is the uncertainty of the teacher itself. So if teacher will be certain about some of its learning, that fraction of learning will be transferred to this contrastive relation matrix. And then when it is transferred, then when the student will learn from logics because we are actually applying care divergence, we are not ignoring it. So a student will learn it using the self-confidence factor, that is its own uncertainty. So that means uh, how much fraction of students this supervised learning is more confident by the student, and how much fraction is more confident in this contrastive learning. So the we are actually applying confidence in two ways. First is that teacher will send the knowledge or transfer the knowledge based upon its confidence. So teacher will say that this much knowledge I am sending with this much confidence. The student will take this knowledge and the knowledge from teacher using distribution gap also. Then student will decide that how much fraction of knowledge I should consider for back propagation among these three. First is this contrastive knowledge, this distribution knowledge from teacher, and its own learning from the data. So based upon that, the student model will back propagate. And at the end of the learning, this student model will be extracted and fully connected layer will be applied on it for the final task, or we can say classification task. So this is a mathematical representation. So first two is supervised contrastive learning equations. So in this, what we have done is that we have p number of positive pairs. For each class I, there is some representation which can work as anchor. And yes, Rahul, you have some question. Please share. So for teachers learning, what we have done is that we are actually utilizing the samples from student for supervised contrastive purpose. So this is one thing, and for student we are utilizing the samples from teacher as a negative pair, and then we actually extract the anchor using aggregation of the samples or embeddings we are learning through non-parametric learning using MS, and AI is the cardinality for ith class. Is there a question I have got? No. Okay. So after extracting the anchor, we will actually apply the relation among the projection of some example through the student with that anchor of the student, and same thing we will do for the teacher as well. And then after extracting this kind of we can say relation, we will actually form a unit vector having this relation between two such relations. So what we are doing, if we are having P and Q, two data points of that student models representations, so what we will do, we will actually calculate the distance between these two, normalize with the help of MSE, and same we will do for P and R, and later we will actually calculate the CRA, that is categorical relation alignment loss, that is uh, some function we will apply on the relation between these two for teacher and the student. Okay, so we are forming the relation between the teacher's data point or embeddings we are getting through different learning, and the student for student we will do the same, and then we will actually calculate the difference between these two embeddings or these two relations or vectors using some function delta. Delta is treated as a uh, some kind of alignment loss. So This may be Huber law, this may be MSC or any other laws. And for uncertainty, we are actually calculating the entropy of student model. For teacher, we will calculate Px. So it is y probability of y given x log probability of y given x for some output, and we take negative of that. So we have two factors, uh, psi 1 and psi 2. First is the uncertainty, second will be the certainty. So ux by u will be telling the uncertainty, 1 minus ux by u will tell the certainty. So the final loss for back propagation will be all the certainties will be added and applied to the weighted cross entropy, because it is a class imbalance scenario. Then there is some weightage for, we can say, distribution based learning, that is the traditional knowledge distillation. Then uh, for uncertainty part, if it is uncertain, then why? So for students contrastive learning, we will actually apply the uncertainty with the student contrastive learning, and then this is the teacher's confidence factor, which we will apply on contrastive relation alignment loss. So this is all the thing we have done here. So this is the overall algorithm that is mentioned in the supplementary of the paper. You can go for the code here. So what I have told is actually written here, that we will actually take as an input, we have the deep neural network S and similar teacher architecture T, and we have the memories. So parameters we want to take is some batches, X belong to capital X, there may be some epochs, there may be some hyperparameters, and there is some output. So we will first load XY to memories and extract test and Y test for testing data, and then initialize some random weights to the student, and then teacher will be initialized with the help of the exponential moving average. But at the earlier stage, at the first epoch, we will be just choosing it randomly. Then we will apply some perturbations, or we can say augmentation on the data, and this is for loop. And for looping purpose, we will just increase I at the end of loop. That is a simple thing we do in algorithms. Then we will do some warm up so that the student learn using its weighted cross entropy as well. Then we will update this W dash, or we can say teachers weightage, using exponential moving average. Then we will extract ZS, ZT, PSPT. PSPT are actually this probabilities, the softmax or soft probabilities or soft logics we are getting after applying fully connected layer on this projection head, or we can just apply just on top of it also. So next we will calculate the anchors with the help of representations, and extract the relations using ZT and ZS. Then you will calculate the unit vectors to calculate CRA, then calculate these losses. All the calculation of losses will be done, and at last we will apply the overall loss function to the student, and update the teacher's weightage, and at last we will just apply this train distill function and test it. So this was overall methodology. So if there is any doubt, okay. So coming to the result part, and the data I have considered. So first data I have considered is Asia Pacific Ophthalmology Society data set, that is APTOS. So there are 3662 fundus images, and these are all for diabetic retinopathy. So there are 5 classes. First is no diabetic retinopathy, then there is mild, there is moderate, there is severe, then proliferative. So from normal eye, we actually get symptom visible. Then there is some uh, woolen spots. Then there is some vision loss. Then there is potential blindness. So there are 5 classes, and you can see the distribution of classes and distribution of data among the classes. There is 1800, 193, 295. There is a significant class imbalance we can see, and there is inter and intra-class relations also. The second data we have considered is actually skin cancer data. So it is International Skin Imaging Collaboration Data, ISIC 2018 dataset. It is also told as Skin Cancer Amnest, also told as HAM 10,000, Human Again Machine with 10,000 images. It is having 7 classes. So these 7 are different kind of skin diseases, which may be treated as a cancers uh, or some diseases which may lead to cancer. So you can also see a significant class imbalance here, like 6705, then 1113, and at last we have 115 also. So we have to deal with such kind of data, and these are real world data sets. We can actually face these problem uh, prevalently in case of medical image classification or medical image analysis. So the performance metrics we have used is accuracy, which is actually proportional of correctly classified instances. So it is not actually suitable for class imbalance, because there may be class bias. If we have 80% data which is of same class and which is classified good or classified right, so we will get 80% accuracy. That will not be suitable, but it can be better for assessment of inter and intra-class relationships of input. So for class imbalance, we may need some other metrics also. That is, we have considered balanced multi-class accuracy, which is actually average of sensitivity and specificity. Then there is mean average precision. So for each class, we actually take the average of precision, and there is recall, there is F1 score, and area under curve. You can see, and these are actually prevalent. These are the functions we actually use for it. So there is BME and MAP is a little new. So you can see the overall uh, formula, n is number of classes. So that is all for performance matrices. Coming to the results part. So for the results, we have actually uh, done different kind of thing. We had actually the data which is having significant class imbalance and inter and interclass similarity, but we want to test it for severe class imbalance. So we have taken this ham 10,000 data and aptos as well, but ham was having more chances for getting this severe class imbalance. So we have created 4 kind of variants of data where there was less class imbalance, there was original data, there was severe class imbalance, and there was some data which may be treated as balanced, because there was some classes which were having some equal number of examples, but we may not be able to treat it as fully balanced, but it is comparatively balanced. So we have actually defined a function rho, which is actually the ratio between the largest class and the smallest class based upon data. So for severe class imbalance, we can see rho is 5364 by 37, and it is for all. So we have calculated accuracy, average precision, recall, and F1 score based upon the previous papers. So you can see that for each of the cases where there is severe class imbalance, our method was working efficiently. For original data, there was a comparable result for recall, but all other things were fine. Then for less class imbalance, again, it is working well. And for very less class imbalance or balanced data, nearly balanced, we have got this kind of result. For all, we are getting either best or second best, and we may actually um we may actually infer that this may be due to better extraction of knowledge, from different sources. And this is another one where we have compared it with with some of we can say prevalent knowledge distillation techniques which are generic, and also some techniques which are dedicated for medical data. Here we have actually compared it, the KD, the recent knowledge distillation method, advanced knowledge distillation method, and these two are actually medical image classification baseline. Then uh, there are some other methods which are this is actually kind of knowledge distillation only. Then there is relational knowledge distillation, there is self-supervised knowledge distillation, then class guided knowledge distillation, then there is CRD, contrastive representation distillation, then SSDKD, where we actually apply the relational transfer of supervised self-supervised learning, then SCLIKD, where we apply uh, supervised contrastive learning itself for intermediate knowledge transfer, but it is not meant for coherent knowledge transfer. It was just knowledge transfer. So there may be a chance that we may improve it. So UDCD is actually improving it. Now, you can see here also, either we are getting the highest or the second highest. Among these two, we are actually calculating accuracy, average precision, then it is actually mean average precision, then BMA, then F1 score, and there are ROC curves as well, where we can see it for different diseases for Aptos. Then coming to the inter and intra-class similarity results, where we have actually plotted the T-SNE plots after training the encoders. So this is how the original data look like. Then when we actually initialized the weights of student, it was untrained. Then at the initial stage, it was looking like this. Then if we have trained it using similar simple data, we can say supervised learning technique, then we have got this one. Then if we apply the knowledge distillation, it is mostly similar to this. Then there was RKD, that is relational knowledge distillation, which is providing a better one, but it's good for uh, largest class, or we can say it is showing class bias. Same for SCLIKD also. CRCKD was little better, or we can say far better. SSDKD was also taking this, and if we see this one, UDCD, we can see that the smaller classes are clustered properly, and the larger classes are actually not scattered like this. These are very close. So that is what we have got. Then these are some other results. We can see that there is a few sort analysis where we have applied some uh, these methods on fraction of data. So 40%, 60%, 80%, 20% was very less. So we have not shown it. And we have compared it with CRCKD and SSTKD, the well-known methods for medical image classification based knowledge distillation. Same we have done for backbone analysis. So for backbone, we have considered five kind of neural architectures: DenseNet 121, ResNet 50, MobileNet, FCNet B0, and B2. All the previous results were calculated on DenseNet 121, but this result we wanted to ensure that it may work as generic. So we have tested it for different neural architectures as well. So this is for Aptos. These all are for Aptos. And then the matrices, when we applied the ablation study, we have got that when we are applying one method, like when we are learning using weighted cross entropy only, we are getting lesser accuracy. Then if we apply uh, the knowledge distillation with only contrastive learning of the student, then we are getting a little better, but a fluctuating one. we are applying this with KL divergence and the contrastive relation alignment, then we are getting better one. And when we are applying all four, we are getting a much better accuracy and all other performance metrics. So at last, if I want to conclude, we can say that UDCD can provide a better solution in case of the inherent problems in medical data like class imbalance and significant inter or intra-class relationships. There were three key innovations introduced: contrastive relation matrix, relational alignment, and relational alignment is done in previous work, but it is for contrastive relation. So it is the novelty. Then there is uncertainty-driven contrastive knowledge transfer, because uncertainty or any kind of adaptive approach are used in different methods, but we have introduced uncertainty as a confidence factor at two levels, and to ensure among different knowledge ways and sources. In the previous work, it was like the knowledge from different teachers. So we are actually extracting the contrastive relation matrix, then we are applying relational alignment on specifically on non-parametric and uh, contrastive aligned learning, and uncertainty driven contrastive knowledge transfer is for we can say for teacher to student, to boost the learning of teacher for its own learning, and the student's self confidence factor, which actually chooses among the different learnings uh, learned from different ways. So these three are the innovations or novelty we have introduced. So it actually mitigated the irrelevant knowledge propagation from both student and teacher models for the back propagation of student. And these innovations can facilitate the distillation of rich structural knowledge from mean teacher model. So overall, if I say that we tried to extracted more and more information in different ways from a mean teacher self-ensembling, using different paradigms, different learning paradigms, and then we calculated the confidence or uncertainty not for different models, but within the model, uh, or we can say within the learning of same model, or learning transfer from a different model. And we have also aligned the relations not among the data points, but uh, from the learned representations we have extracted through contrastive and non-parametric learning. So that is all for UDCD. The limitations of this work is that it is checked for image classification only and single mode of data. So in future works, we may consider it for different tasks, make it generic, uh, or we can say we can test its generosity and for multimodal. And also we can see some scope for federated distillation also, where the data is private at different clients, and there is a active learning approach where the data is learned in the real time or captured in the real time. Then data heterogeneity, which is actually done uh, actually a problem in case of federated learning. So we want to acknowledge Prime Minister's fellowship also, that is from Government of India, that facilitated the execution of this research work. So thank you from my side. If there are any questions, I will be happy to take.
Thank you so much, Saurabh, for the good presentation and for the introduction to the topic. And yeah, if you guys have any questions, please feel free to ask either by raise your hand and then I unmute you guys, or you can ask in the Q&A section, typing down the question. So I give you some minutes. And I have one question, Saurabh, regarding your work. Uh,
Yeah.
it's quite nice that
So
you can get the relationship between the different diseases. Were you able to qualitative or quantitative to see if diseases from the same family are close together or they share some relationship. So, for instance, in the ham dataset, you have actinic keratosis and seborrheic keratosis. So, are these diseases closer together, or do they share a relationship in the embedding space?
Um, please, can you please repeat, Alvaro? Actually, I got disconnected in between.
No problem. So
Yeah.
you work with two data sets, the
Yes.
ham dataset and Aptos. So
Yes.
in the ham dataset, you can see you have two classes that belongs more or less in the same family. One is
Yes.
actinic keratosis, and the other one is benign keratosis or seborrheic keratosis. So
Yes. Yes.
do you see in the embedding space that these two classes are related to each other, or like they are similar or closer in the embedding space?
These are actually similar when we see it from naked eyes, or we can say in the images or the data we are getting. So in the embedding space, if we will, it's my opinion, if we will just encode it using some neural network, it may be looking closer to each other. But if we will go through different perspectives, like I have used, like we have two perspectives. One is non-parametric, second is contrastive. So there may be some difference in different perspective of seeing it, or the embedding we are getting from the data in different perspectives. So that may actually differentiate among those examples. Okay. Am I clear? Or
Yes, yes, you're clear. Then,
yeah.
do you think it's possible to add any of the metadata that you have in the datasets to train the model and to improve the classification results,
Yes. Yes.
like
Sure.
the body
Sure.
localization or the, I don't know, the skin color or the gender, the age of the patient?
Yes, actually, we can. As I have told in the future scope, because we have tested it for simple single mode. So when we can add metadata, or we can go, we can say for multimodal setting, that will be always beneficial, because we are getting only image. And if we will consider label, that is good. If we will not consider label, that may be harmful, or if, for a time being, if we just consider that labels are noisy, then we will go to a misclassified result. So in that case, metadata or any kind of multimodal information will be beneficial.
That's good. Thank you so much, Sarah. So I see that there are
Thanks.
no other questions. So your presentation was very clear to the audience. So that was very good. So then we leave it here. Thank you so much again, Saurabh, for the presentation. And
Yeah.
I hope to see you in this MICCAI or in 2025 in Korea.
Yeah, sure. I will try.
Have a nice weekend and thank you so much. Bye bye.
Yeah. Yeah. Thanks, everyone. Thank you.